Students, in the previous class, we were discussing trigonometric equations, a few case-set questions. A few are left off. We will complete that so that we can go to the next PU chapter. So, question number 11, we did up to question number 10. It's given that sine x by cos x into secant x by cosecant x into tan x by cot x is equal to 9, where x is between 0 and pi by 2. That means in first quadrant, all are positives. The value of x you have to find. So to simplify this, I will take sine x by cos x into secant x. I will write 1 by cos x, cosecant x 1 by sin x, tan x as sin x by cos x, and cot x as cos x by sin x equal to 9. So I can write sin x by cos x into 1 by cos x into sin x by 1. I'll take the reciprocal. And sin x by cos x into sin x by cos x, reciprocal again, equal to 9. So I can write sin x by cos x into sin x by cos x into sin square x by cos square x equal to 9. So total I have sin power 4x by cos power 4x equal to 9, or sin x by cos x whole power 4 is 9. That means I can write sin square x by cos square x is square root of 9. That is sin square x by cos square x is 3. And sin x by cos x will be root 3. Tan x will be root 3. That means x has to be pi by 3. So if you are good at all trigonometric ratios, values, it will be easy for you. Question number 12. You have to find principal solution of root 3 secant x equal to minus 2. So secant x is minus 2 by root 3. Cos x is minus root 3 by 2. If it is cos x equal to root 3 by 2, you can write x will be pi by 6. But because it is negative cos x will be negative in the second quadrant. That means pi minus pi by 6 you have to take. So x will be equal to 5 pi by 6. Next is question number 13. You have to find number of roots. You are given a matrix sin x, cos x, cos x, cos x, sin x, cos x, cos x, cos x, sin x equal to 0. And the interval for x you have to take minus pi by 4 to pi by 4. Between minus pi by 4 and pi by 4, or you can take minus pi by 4 to pi by 4. So first we will solve this matrix. In order to solve this matrix, this is row 1, this is row 2, this is row 3. I will do row 2 minus row 1 and row 3 minus row 1. That means I will not change row 1. But rho 2 minus rho 1 will give me cos x minus sin x. Rho 2 minus rho 1 will give me sin x minus cos x. And cos x minus cos x is 0. Similarly, rho 3 minus rho 1 will give me cos x minus sin x. Cos x minus cos x is 0 and sin x minus cos x here equal to 0. Now, I can take cos x minus sin x common from rho 2 and from rho 3 another cos x minus sin x I can take common. So rho 1 did not change at all. It remains the same. Here when I take cos x minus sin x common from rho 2, 1 and here it will be minus 1. Then here see. From rho 3 also I am taking cos x minus sin x. Good. So here 1, here 0, but here it will be minus 1 equal to 0. So I have cos x minus sin x whole square and this I will expand sin x into, I have to multiply these two and these two. So 1 minus 0 minus cos x plus sin x over, now minus cos x into, I have to multiply these two. So minus 1 minus, I have to multiply these two. So 0. Lastly, plus cos x into, now I have to multiply this 0 minus this minus 1. So it will become plus equal to 0. So that is cos x minus sin x whole square into sin x here plus cos x here another cos x equal to 0. Or I can write cos x minus sin x whole square into sin x plus 2 cos x equal to 0. I can take cos x minus sin x equal to 0. I can take sin x plus 2 cos x equal to 0. So cos x is equal to sin x or tan x equal to. Here sin x equal to minus 2 cos x or tan x equal to minus 2. Tan x cannot be minus 2 because x is, if you take, x is between minus pi by 4 and pi by 4. So tan pi by 4 is 1. Tan minus pi by 4 is minus 1, 0. So tan has to be between minus 1 and 1. So tan x cannot be 2. But tan x is equal to 1 means x will be pi by 4. This will hold correct. So with this we have completed trigonometric equations case set questions. Now we can go to PU. In PU already we have done 3 chapters. Now today we can go with the 4th chapter. The 4th chapter is mathematical induction. Actually, mathematical induction doesn't have much theoretical part. It has only problems. In mathematical induction, you will be given a statement. You will be given a statement in terms of n. And then you have to show whether this statement is true or false. So your first step is, and you will put 1 into the statement. Observe carefully. Use the formula which they have given. For P of n, whichever formula they have given, use it. Then you can observe and see whether this is true or false. You will get it true. Now, second statement, second thing you have to do that, assume that for n equal to k, when you put it in the statement, it has to be true. Just blindly, don't do any work. Close your eyes and say that this is true. Don't prove anything, don't show it. The third work you have to do is put n equal to k plus 1 in the polynomial and prove that it is true using the previous p of k. If I say this, you may not understand. But when we do problems, you will be able to understand. For example, first question. For n greater than or equal to 1, the statement given to you is 1 square plus 2 square plus 3 square plus 4 square up to n square. The formula is n into n plus 1 into 2n plus 1 by 6. Now this statement is true or not. That is your work to prove. So first, what did I tell you? Put n equal to 1. For n equal to 1, the statement p of 1. When you put n as 1 on left hand side, you will have only 1 square, that is 1. Right hand side, when you put n as 1, 1 into 1 plus 1 into 2 plus 1 by 3 by 6. And that is 2 into 3, 6 by 6 equal to 1. So left hand side of the formula 1, right hand side of the formula 1. So you can say for n equal to 1, left hand side, right hand side are equal, means the statement is true. You have proved. The second work you have to do is for n equal to k, assume in the statement when you plug k, when you substitute k, it is true. Close your eyes, blindly say it is true. Don't prove anything. That means P of k, the left side 1 square plus 2 square plus 3 square plus 4 square plus k square is same as k into k plus 1 into 2k plus 1 by 6. I did no work. Just copied the entire question left side and right side by putting n equal to k. So third work is for n equal to k plus 1. You take p of k plus 1, but take only left hand side. Because here you have to do lot of work. You have to prove. Left hand side you will have 1 square plus 2 square plus 3 square plus 4 square, like that. N is k plus 1 whole square. But before k plus 1 whole square, you will have k square also. So now you have to use p of k. That means up to k square. 1 square, 2 square, 3 square, 4 square up to k square. Already you have assumed that it is k into k plus 1 into 2k plus 1 by 6. This is how you will use P of k. And then I will write k plus 1 whole square. I will take k plus 1 common. So when I take k plus 1 common, k into 2k plus 1 by 6. Left is k into 2k plus 1 by 6. And here left is k plus 1. 1k plus 1 taken, 1k plus 1 left. Now you take common denominator 6. K into 2k plus 1 plus 6 into k plus 1. This is what you have. Simplify it further. 2k square plus k plus 6k plus 6 by 6. Or k plus 1 into 2k square plus 7k plus 6 by 6. Or k plus 1 into, rationalize it. You will have k plus 2, factorize it. When you factorize it, you will have k plus 2 into 2k plus 3 by 6. This is the answer for left side. Now on right side also you put n as k plus 1. So what do you have? N, k plus 1. N plus 1, k plus 1 plus 1. See, on the right side you have n, n plus 1, then 2n plus 1. So 2 into n, which is k plus 1 plus 1 by 6. That means you'll have k plus 1, k plus 2, 2k plus 3 by 6. You can see left hand side answer and right hand side answers are same. That means you have proved by principle of mathematical induction. This is only called principle of mathematical induction. It is proved for n greater than or equal to 1, P of n is true. This is how every problem in this mathematical induction topic, you have to prove that. Let's go to question number 2. Prove that 2 power n is greater than n for all n belonging to set of positive integers. So first what we have to do? For n equal to 1. What is the statement here? 2 power n is greater than n. So we will take P of 1. That means we will take left hand side 2 power 1. Okay, which is 2. And right hand side we will put n equal to 1. So we have proved that left hand side is greater than right hand side. That means we have shown that P of 1 is true. Now second, you have to assume that P of k is true. Blindly close your eyes. We are assuming here. We are thinking here. We are not proving anything. For P of k is true. That means P of k, what is P of k? 2 power k is greater than. Now for the third one, we will take n equal to k plus 1. So we will take left hand side. 2 power n, that is 2 power k plus 1. This 2 power k plus 1, I will take 2 power k into 2 power 1 or 2 power k into 2. Now I know that I will have to use p of k because 2 power k is greater than k. So what I will write? 2 power k is greater than k. 2 I will write same. I'm using that. So I'm saying 2 power k plus 1 is greater than 2. Or I'm saying 2 power k plus 1 is greater than k plus k. 2k I'm writing that. So I can say 2 power k plus 1 is greater than this k, and instead of this k, 1. So as we have proved 2 power k plus 1 is greater than k plus 1, isn't it looking like 2 power n greater than n? It's looking same, 2 power n greater than n. That means we have proved that p of k plus 1 is true for all n belonging to set of positive integers by principle of mathematical induction. We will go to question number 3. For all n greater than or equal to 1, prove that 1 by 1 into 2 plus 1 by 2 into 3 plus 1 by 3 into 4 plus 1 by n into n plus 1 is equal to n by n plus 1. So this we will take as the statement P of n. First, you have to take n equal to 1. In P of 1 you have to find. For that, left hand side you will put n as 1. 1 by 1 into 1 plus 1. 1 by 1 into 2. That is 1 by 2. Right hand side also I will put n as 1. Here 1 by 1 plus 1. So I got left hand side equal to right hand side. That means P of 1 is true. Next step. What is the second step? Assume for n equal to k, P of k is true. Blindly, P of k is true. That means what is P of k? Left side is 1 by 1 into 2 plus 1 by 2 into 3 plus 1 by 3 into 4, and so it goes up to 1 by k into k plus 1 equal to k by k plus 1. Everywhere in place of n, I have put k and blindly saying it is true. But now for n equal to k plus 1, I will take P of k plus 1 but left hand side. On left hand side I have 1 by 1 into 2, 1 by 2 into 3, 1 by 3 into 4, and it goes on. I will put n as k plus 1. 1 by k plus 1 into k plus 1 plus 1. But before this I have to put n as k. K into k plus 1. 1 by k into k plus 1. But from P of k, this entire thing, This entire thing can be written as k by k plus 1 equal. Then I have plus last one 1 by k plus 1 into k plus 2. I will take common denominator k plus 1 into k plus 2. Left is k into k plus 2 plus 1. Or I have k square plus 2k plus 1 by k plus 1 into k plus 2. Or I have to factorize the numerator. K plus 1 whole square by k plus 1 into k plus 2. That is what I have. So what happens? 1k plus 1 cancels. I have k plus 1 by k plus 2. But on right hand side, if you put n as k plus 1 by k plus 1 plus 1. That is k plus 1 by k plus 2. Because I got left hand side answer and right hand side answer same, I can say by principle of mathematical induction, P of n is true for all n greater than or equal to 1. I think by this time you are comfortable. More examples we will take so that you will feel better. More questions. Fourth one. For n, which is a positive integer, prove that 7 power n minus 3 power n is divisible by 4. Is divisible by 4. Divisible by 4 means what? It should be multiple of 4. So the statement I will take is 7 power n minus 3 power n should be multiple of 4. Then only it will be divisible by 4. So first I will put n equal to 1 for n equal to 1. I will take p of 1 but left hand side first. 7 power 1 minus 3 power 1. That is, it is 4. Whereas right hand side, what I have? Right hand side 4m. So this is multiple of 4. 4 into 1. It's a multiple of 4. So left hand side equal to right hand side. That means P of 1 is true. Next, second what we have to do, for n equal to k, directly you have to assume that P of k is true. That means you will take directly closing your eyes, put any scale. 7 power k minus 3 power k is divisible by 4, is multiple of 4. That you are putting directly. Now the third part you have to prove here. For n equal to k plus 1, we will take p of k plus 1. But first we will take left hand side. In place of nk plus 1, in place of nk plus 1. But I can make some changes here. What are the changes? I'll write 7 power k into 7 minus 3 power k into 3. Now what I have to do? 7 power k I can take from the P of k and write it as 4m plus 3 power k into 7 minus 3 power k into 3. So what do I have? 4m into 7. 3 power k into 7 minus 3 power k into 3. 4m into 7, 3 power k common, 7 minus 3. 4m into 7 plus 3 power k into 4. I can pull out 4 common, 7m plus 6 power k is left. So that means I got this nothing but multiple of 4. 4 into m. Some multiple of 4. I got it. That means I can say by principle of mathematical induction, the statement is true. Okay? For all n belonging to Z, set of positive integers. Let's go to question number 5. Prove that 1 plus x whole power n is greater than or equal to 1 plus nx for n belonging to set of natural numbers and x is greater than minus 1. For this you have to prove. So we will take the P of n statement as 1 plus x whole power n is greater than or equal to 1 plus nx. Now we will take n equal to 1. First one, work n equal to 1. That means P of 1. We will take left hand side 1 plus x power 1. That is 1 plus x. We will take right hand side n equal to 1. 1 plus 1 into x. That is 1 plus x. So you can say left hand side, instead of saying greater than or equal to right hand side, it is equal. Greater than or equal, anything will do. So instead of writing greater than or equal, I will just write equal. In that way also I have proved P of 1 is true. Now our second work is assume for n equal to k, P of k is true. That means we are assuming 1 plus x whole power k is greater than or equal to 1 plus kx. This is just assumption. Now the third is we will take n equal to k plus 1 and we will find P of k plus 1. I will take left hand side 1 plus x power k plus 1. But I can write this as 1 plus x power k into 1 plus x. This 1 plus x power k from P of k, I can say it is greater than or equal to 1 plus kx. So greater than or equal to 1 plus kx. But this 1 plus x will be same. This is what I am changing. I am using P of k. In P of k, what do I have? That I am using. I have 1 plus x whole power k is greater than or equal to 1 plus kx. I am writing this one as it is. So I can write 1 plus x power k plus 1 is greater than or equal to, when I multiply I have 1 plus x plus kx plus kx square. And I can write this will be obviously greater than or equal to just 1 plus x plus kx because I have removed this. So finally I can write 1 plus x power k plus 1 is greater than or equal to 1 plus x plus kx. Isn't it? This is what I can write. Or in other words, I can write 1 plus x power k plus 1 is greater than or equal to 1 plus x outside k plus 1. So this is looking nothing like what's given in the question. What is given in the question? 1 plus x power k is greater than or equal to 1 plus kx. That's what we have to prove. Next, question number 6. Prove that 2 into 7 power n plus 3 into 5 power n minus 5 is divisible by 24. So we will take P of n statement as 2 into 7 power n plus 3 into 5 power n minus 5 is multiple of 24. Now first one, for n equal to 1, we will take P of 1. We'll take left hand side 2 into 7 power 1, 3 into 5 power 1 minus 5. That is 14 plus 8 minus 5. Sorry, this is not 8, this is 15. 14 plus 15, 29 minus 5, 24. It is multiple of 24. That means P of 1 is true. Now your second work is assume for n equal to k, P of k is multiple of 24. P of k means what? 2 into 7 power k plus 3 into 5 power k minus 5 is multiple of 24. That is what we are proving. Now the third part we have to prove for n equal to k plus 1, P of k plus 1. So left hand side 2 into 7 power, in place of n I have k plus 1 minus 3 plus 3 into 5 power k plus 1 minus 5. I have to prove this is a multiple of 24. So I'll write 2 into 7 power k into 7 power 1, 3 into 5 power k into 5 power 1 minus 5. That means I have 14 into 7 power k plus 15 into 5 power k minus 5. 14 into 7 power k. How will I write this 7 power k? 24m minus 3 into 5 power k plus 5 by 2 plus 15 into 5 power k minus 5. So 2 ones, 2 sevens will cancel. 7 fours 28, 7 twos 14 and 16 minus 21 into 5 power k plus 35 plus 15 into 5 power k minus 1. This is what I have. Now I will write 168m minus 21 and plus 15. Minus 21 and plus 15. What I can write? I can combine both. What I mean is, I will combine this and this. So minus 6 into 5 power k. And 35 minus 5 is 30. This is what I have. I have 168m minus, what do I have next? 6 into 5 power k plus 30. I have to show that it is multiple of 20. So what I will do? I will take 168m minus 6 I will take common, 5 power k minus 5. This is what I have. Now, I will take 5 power k minus 5 separately. I have a new question. I have P of n a statement 5 power k minus 5. 5 power n minus 5 I have. For n equal to 1, P of 1 I can write 5 power 1 minus 5. That is 0. For n equal to 2, I will write P of 2 is 5 power 2 minus 5. That is 25 minus 5. That is 20. So I can say it is multiple of 4. So I can take for n equal to k, P of k is multiple of 4. That means I can take 5 power k minus 5 is multiple of 4. I can take it like that. For n equal to k plus 1, when I take P of k plus 1, what do I have? 5 power k plus 1 minus 5. I am taking left hand side. 5 power k into 5 power 1 minus 5. Instead of 5 power k, I can use this. 4m plus 5 into 5 minus 5. 20m plus 25 minus 5. 20m plus 20. 4 into 5m plus 5. So this is multiple of 4. Four into something, 4m. It's multiple of 4. So coming back to our question. Where did we leave the question? We'll start there. 168m minus 6 into 5 power k minus 5 is multiple of 4. I will take 24 outside. When I take 24 outside, I will have 7m minus m. So it's multiple of 24. So I can say P of n is divisible by 24 by principle of finite mathematical induction. I'm introducing finite also. Principle of finite mathematical induction. Next, we can go to question number 8. What does question number 8 is asking? Oh, we left question number 7, I think. 6 we did. Yes, 7 we have to do. Question number 7. What does it say, question number 7? Prove that the principal statement, the statement is 1 square plus 2 square up to n square is greater than n cube by 3 for all natural numbers belonging to set. So first in the statement, I will put n equal to 1. And for finding p of 1, I will take left hand side. 1 square plus 2 square plus 3 square up to, because n is 1 square. That means I need not take all these. N is 1 means left hand side, when I put n equal to 1, here, I'll have only one term, 1 square, which is 1. Now right hand side, what I should take? I have to take 1 cube by 3. 1 by 3. We know left hand side is greater than right hand side. That means P of 1 is true. Next, second one, we have to assume for n equal to k, P of k is true. Blindly think. That means 1 square plus 2 square plus 3 square up to k square, n is k, is greater than or equal to k cube by 2. Because it's true. Greater than. Equal to, you need not write. Okay, now third, we will take n equal to k plus 1. That is left side of pk plus 1. We will take left hand side. 1 square plus 2 square plus 3 square up to k square. The next one is k plus 1 whole square. But if you use n equal to k, all these 1 square plus 2 square up to k square, you can write this is greater than or equal to k cube by 3 plus extra k plus 1 whole cube. Isn't it? So here I can write k cube plus 3 greater than or equal to k cube plus 3 into k plus 1 whole cube by 3. Or greater than or equal to k cube plus 3 into k cube plus 3k square 1 plus 3k square into 1 I'm doing. Plus 3 into k into 1 plus 1 cube. By 3 I have. Or I can write this as k cube by 3. This is k plus 1 whole square. It was not visible clearly. So I'm explaining here again. Listen carefully. When I put n equal to k plus 1 on the left hand side, I have 1 square plus 2 square plus 3 square plus k square, isn't it? I have this. So I can use this p of k and write it is greater than or equal to k cube by 3. But this k plus 1 whole square is there, extra. That means I can write greater than or equal to k cube plus 3 into k plus 1 whole square by 3. Or k cube plus 3 into k square plus 2k plus 1 by 3. Or k cube plus 3k square plus 6k plus 3 by 3. Now I can make some changes here. Because I have k cube, I must have 3k square into 1. I have. Then I must have 3k into 1 square. So for that, what I will do? From 3k, from 6k, I will take 3k and 3k separate. So I'm using 1 3k here. Then what I must have? I must have 1 cube. So what is left? This 1 3k is left. And 3 I'm writing as 1 plus 2. 1 cube already I've taken, so 2 will be there. I'm doing all these because I want to get some form. Which form I'm trying for that. Once I get that form, even you will be able to understand. So this I can write all these throughout as k plus 1 whole cube. Because I'm writing on left side, k plus 1 whole cube is k cube plus 3k square into 1 plus 3k into 1 square plus 1. That is why I changed the form so that I can use this form. K plus 1 whole cube plus 3k plus 2 by 3. That means this is greater than k plus 1 whole cube by 3 because 3k plus 2 extra is there. So we have taken left hand side. If you take right hand side, you will have k plus 1 whole cube by 3, the same thing which we got. So finally you can write, by principle of finite mathematical induction, P of n is true. For all n belonging to n. Next, we will do one more question and then we will go to exercise 4.1. Actually, in this chapter, you have only one exercise. Okay, question number 8. Question number 8 says, prove that AB whole power n equal to A power n B power n for all natural numbers. So the statement we will take is AB whole power n is A power n B power n. First we will put n equal to 1 to find P of 1. Left hand side is AB power 1 that is AB. Right hand side is A power n into B power 1, that is A. So left hand side and right hand side are same. So the statement is true. P of 1 is true. Second, assume that for n equal to k, P of k is true. That means AB power k equal to A power k, B power k. Directly I'm writing without proving anything. Closing my eyes. Now I will take n equal to k plus 1. That is, I'm going to find P of k plus 1. But I will take just left side. Left side is AB power k plus 1. Which I can write it as AB power k into AB power 1. Now AB power k I can use from P of k. And I can write it as A power k, B power k into A. Did you understand what I'm doing? I'm using P of k. In P of k, this is written as A power k into B power k into AB I'm writing. So what I got? A power k plus 1 into B power k plus 1. This is what I got. Right hand side also I will put n as k plus 1. So A power k plus 1, B power k plus 1. You can see left hand is equal to right hand side. LHS equal to RHS. That means by principle of finite mathematical induction, the given statement is true for all natural numbers. So with this, we can go to exercise 4.1. We have only 2 minutes left. So in this 2 minutes, we can complete one problem. So we will do that first problem, exercise 4.1. Next class, we will complete all. The first question and all questions actually are proved by principle of mathematical induction. Proof by principle of finite mathematical induction for all natural numbers. So first question, if you take the statement P of 1, you can take as 1 plus 3 square up to 3 power n minus 1. Equal to 3 power n minus 1 by 2. So if I take P of 1, left hand side, 1 plus 3 plus like that, I have to take n as 1. N as 1 means take the last term. In the last term, when you put n as 1, what you will get? 3 power 1 minus 1. 3 power 0. That is 1. Left hand side. Right hand side, what you will get? 3 power 1 minus 1 by 2. 3 minus 1 by 2. 2 by 2. That is 1. Because left hand side is equal to right hand side, I can say P of 1 is true. Now next, what I have to assume? Assume for n equal to k, P of k is true. What is P of k? 1 plus 3 square up to 3 power k minus 1 equal to 3 power k minus 1 by 2. This is P. Now for n equal to k plus 1, we will take P of k plus 1, but we will take only left hand side. 1 plus 3 square up to 3 power k minus 1, then 3 power k plus 1 minus 1. Because n I am putting as k plus 1. This is left hand side. But this entire thing from P of k, I can write 3 power k minus 1 by 2. Then I have plus 1 and minus 1 will cancel 3 power. So 3 power k minus 1 plus 2 into 3 power k by 2. Or I can combine these two and I can say 3 into 3 power k minus 1 by 2. That is 3 power k plus 1 minus 1 by 2. On right hand side also I will put n as k plus 1. 3 power k plus 1 minus 1 by 2. I got the same answer. Left hand side answer and right hand side answer. That means P of n is true by principle of mathematical induction for all n belonging to set of natural numbers. So with this we will end our class. In the next class we will go to question number 2 of this exercise. See you in the next class.